Hello, it's Paul with a script designed to show you the connection between infinite series and their partial sums. So let's start out with a slowly convergent series. The general term is 1 over n to the 3/2 power, and I call this slowly convergent because neither the ratio test nor the root test will prove that it converges. As usual, I define the series as a function so that conceptually there are an infinite number of terms, but then I'll immediately generate the first 100 terms as a vector, set up my screen with maximum space around the edges, and plot the terms of the series, and you can see they go to 0 fairly quickly, which is characteristic of any convergent series. Now we'll calculate the partial sums, which are really the important thing. Set up a vector to hold 100 of them, and fill the nth element of this vector with the sum of the first n elements of the series. And let's plot these. This type equals s plot is kind of useful. It's a staircase plot, and it gives you something that looks like a continuously interpolated graph. Well, this series kind of looks as though it converges because the partial sums appear to be approaching a limit. Let's see if we can get a better idea of that. We sum the first 1,000 terms, 2.54. Sum the first 10,000, 2.59. Sum the first 100,000, 2.60. And I can draw a line at 2.61. This is almost certainly an upper bound, and the limit of the partial sums is somewhere between 260 and 2.61, I'm fairly sure. Summing series is a tricky business, and usually there's no formula that tells you the answer. So that was a convergent series. Let's look at one that diverges to plus infinity. All I have to do is change the function so that now the nth term is 1 over n to the 0.9. I'll plot 100 terms of that. They go to 0, though not so quickly. And as soon as you compute and plot the partial sums, you see what the problem is. These partial sums just keep getting bigger and bigger and bigger. This series does not converge. The partial sums get larger than any positive number you may choose. However, we can fix things. If we change the signs on all the even-numbered terms, we'll get an alternating series which converges very nicely. So the -1 to the n plus 1 power puts a plus sign on all the odd-numbered terms, a minus sign on all the even-numbered terms. And when you look at those, you can see the alternation of positive and negative terms, with the absolute values getting smaller and smaller. That's characteristic of an alternating series. When I compute the partial sums and plot them, you can see what's going on. The partial sums are alternately larger than and smaller than some obvious limit whose numerical value I just plain don't know. But you can see that the partial sum goes above and below the limit. The limit superior goes down to the limit inferior goes up to the limit, and we have a nicely alternating series that converges. Now let's move on to the root test. The root test, when carefully stated, involves not the limit of the nth root of the nth term, but rather its lim sup, the limit of the supremum. And I'm going to construct a series for which that becomes important. This lim sup is known in Ross as alpha. If alpha is less than 1, the root test says the series converges, and I'm going to choose 0.8, but all that really matters is I've chosen something that's less than 1. So if the lim sup of the nth root is 0.8, that means sooner or later it's going to be less than 0.9. It could be quite a bit less, but anything bigger than 0.8 will do just fine. And now I can construct a function for an infinite series that will pass the root test. What I'm going to do is, for the nth term, generate a random number. It's somewhere in between 0.7 and 0.9. And then, since that's the nth root, I'm going to raise it to the nth power, which makes all the difference. Let's generate 100 terms of this series, plot them, and see what we've got. And you can see the terms get smaller and smaller. They don't go smoothly to 0. That's because the minimum possible value involves 0.7 as the exponent. But once you get fairly far along, that nth power of anything in between 0.7 and 0.9 really makes the term kind of small. And when you calculate the partial sums, you see exactly what's going on. They get up to some level, and they're basically stuck there, and there's not a term that can make them much bigger. So now let's look at an example where the root test reveals that a series is divergent. Now I have to pick an alpha that is greater than 1. I'll choose 1.02. That's a little bit bigger than 1, but it's enough to do the job, because if the lim sup of the nth root is 1.02, that guarantees us that the nth root itself will be bigger than 1.01 infinitely many times. If it weren't, of course, the lim sup would be 1.01 or less. I remind you that this is only the lim sup. Nobody says that the limit is this, and so it's entirely reasonable for some terms to be a lot less than that. So now let's compute a series that will fail to converge because of this. I'm going to generate for the nth root a random number that's somewhere in between 0.7 and 1.01. And then, since that's the nth root, I'll raise it to the nth power to get the nth term. Generate 100 of these, and let's see what they look like. Well, when you look at them, it's immediately obvious what the problem is. For some of these terms, the random number that was generated is bigger than 1. And when you raise a number bigger than 1 to the nth power, you get something that's absolutely enormous, and this is going to happen infinitely often. So we will get not only some occasional big terms, but infinitely many of them. When we add up the partial sums, you can see that there are these big jumps, and the big jumps are just going to keep getting bigger and bigger, and there are infinitely many of them. This series clearly diverges to plus infinity, and that's how the root test is working when alpha is greater than 1. Finally, let's look at a couple of series where the root test and the ratio test both fail to give any useful information because the limit of the nth root of the nth term is equal to 1. We'll start with the so-called harmonic series, where the nth term is 1 over n. In this case, because the function that defines the series has no random number generator in it, it's easy to generate a vector with the first 200 terms. When we plot it, they go smoothly to 0, no big surprise. We can try the root test on this. We have to raise each term to the 1 over nth power. And there's no surprise in the result here either, because we already proved that the limit of n to the 1 over n power is equal to 1. Here we're dealing with the inverse of that quantity, so we're approaching the limit 1 from below, but the general principle still holds true. If I draw a red line at the value 1, the limit stays below that. So alpha's 1, the root test tells us nothing useful. But we can solve that problem. Let's look at the partial sums. So yet again, I put the nth partial sum equal to the sum of the first n terms of the series, and as soon as I plot these, it becomes evident what's going on. These don't even form a Cauchy sequence. And I can prove that by using an epsilon that's not tiny. It's 1/2. Suppose you propose n equals 30. Okay, there's n equals 30. All I have to do is show you that the terms beyond the 30th term don't lie within a band where the difference of two terms could not possibly exceed epsilon. So I add epsilon to the 30th term, and it's clear. If you go far enough along, there's a term that differs from the 31st term by more than epsilon. You can try again, but you're going to lose. You try n equals 90, and again, I put a band at the 91st term plus epsilon, and subsequent terms of the series exceed that. I can express this argument directly in terms of the series, though I think, as you've probably realized, everything is best visualized in terms of the partial sums. Nonetheless, you choose 30. I say, I'm going to sum the terms from 31 to 60, and the sum, as you'll see from the bottom left pane, is 0.684. You say, okay, I'll choose 50. I sum the terms from 51 to 100, and the result exceeds 0.688. And what I'm showing you here is that for the sequence of partial sums, there's a difference in two terms beyond your chosen term that exceeds epsilon. That's enough to prove that the Cauchy condition is not satisfied. You make one last feeble attempt at 80. I sum the terms from 81 to 160, but now you have a chance to show off. Are you aware of any famous number that's pretty close to 0.69? Of course, the natural log of 2. And if you want to see why that's so, you'll have to think about integrals, which are not really going to be very important this term, and realize that the sums I've been giving you are Riemann sums for an integral whose value is very close to the natural log of 2. It's not hard at all to convert this general argument into a proof that the series sum of 1 over n diverges. This proof is useful because this is a case where neither the root test nor the ratio test does us any good. Now let's look at a similar but otherwise quite different argument to show that if I take the sum of 1 over n squared, I have a convergent series. Here I'm going to start with a sequence that converges to 2. The general term is 2 minus 1 over n, and when I plot that, it's quite clear that that series is approaching a limit of 2. Strictly speaking, I've got a sequence, and now I have to form a series for which this sequence is the partial sum. I'm going to put 100 terms in this series, set the first one equal to 1, set the second one equal to the second partial sum minus the first, the third one equal to the third partial sum minus the second, and so on. And I crank out as differences of terms in the partial sums a series that sums to my original sequence. I never quite trust my coding, so I check that I've got this right by printing out the 60th term of my original sequence and the sum of my new first 60 terms of the series. Now for comparison, I'm going to form a series of inverse squares. The general term, the ith term, is 1 over I squared, and I'm going to plot this. Now watch carefully, because I have plotted this in red. The red bar extends up along the blue bar, but it never obliterates the blue. What that means is the series represented by the red terms is term by term no larger than the series represented by the blue terms. And what that means by virtue of the comparison test is that the series that I've just constructed, the series of inverse squares, must converge. If you want to see this in terms of partial sums, it's easy to do. I crank out the partial sums, and you can see that the partial sums are less than the partial sums for my original series. In this case, remarkably, someone has figured out the sum of the series. This was done by the great Swiss mathematician Leonhard Euler in the 18th century. He calculated that the sum was pi squared over 6, and sure enough, if we plot a horizontal line at the value pi squared over 6, it looks like a very reasonable least upper bound for the partial sums. And it's not hard to convert this argument into a proof. Very easy to convert the argument that the series converges, and not too hard to show that what it converges to is actually pi squared over 6.